everybody. Thank you to Cluj for inviting me to share this research project with you. It's something that we're really excited about at my office, and I guess I can get right into it. So we're calling this Printers Without Borders because that's essentially what we're trying to do. We're trying to free your conventional 3D printer from the borders or the confines of its housing that it's constantly constrained to. So this is an artist's rendition of my daily activities at my office. So I'm an architect. I have no engineering background, no robotics background. I spend my days designing and detailing commercial office buildings, mostly at Playa Vista. So the biggest problem with conventional 3D printers that we encounter is just you're always limited in the X, the Y, and the Z directions. We use 3D printers all the time in architecture, and we're always frustrated when we want to build a larger object to study at a bigger scale, and we can't, or we have to break the object in half and then bond it together later, and you get these seams, and nobody's happy with that. So what people have been doing is building bigger and bigger printers. This is research being conducted at USC to 3D print homes, and their research is really incredible, but they're still not solving the problem of the limited build size. The other way that people are doing it is they're building components again in smaller pieces and then transporting them and craning them into the different locations. This is work by Winsun Enterprise in China. So the question is really simple. Would it be possible to remove the constraints of your conventional 3D printer? Give yourself unlimited X, Y, and Z axis control. And with that, my partner Tam Tran, who unfortunately was not able to be here tonight, we went to Gensler and asked them, said, hey, would you be interested in funding this research project? They graciously accepted, not having any idea what we were talking about. So for that, we're ever grateful. And we started off by looking at different robotic platforms. We looked at hexapods or hexabots. They offer really good mobility. They're strong, decent battery life, but there's no Z-axis freedom. We're still confined. So then we said, okay, rovers, that's the next best thing. No, but still, like the Z-axis is our big constraint. And then when we started this research, it was right about when there were a lot of TED Talks coming out with multi-rotors. It hadn't quite hit the mainstream yet, but the DJI Phantom had just been released, and people were starting to talk about it. We saw some videos of these tossing pendulums back and forth between each other, all controlled by the processors on board, and we said, hey, maybe we can just attach a 3D printer to the bottom of this and we'll get that X, Y, and Z axis freedom that we've been looking for all along. So our year one of research, which we typically spend our nights and weekends doing, we ended up putting this together. This was Muppet version 1.0. And what we did was simply take apart your traditional rep-rap, homebrew 3D printer and attach it to the bottom of a UAV. In this case, we didn't design our own UAV. We're using off-the-shelf components that are all knockoffs of the popular DJI stuff from Korea. But it worked great. The biggest problem we had was with the material we were using. We were relying on your conventional 3D printing material. We're using PLA plastic. And that was when we realized, there's a lot of potential with this research, but we need to stop trying to replace your desktop printer. We're not gonna be able to do that. We don't have the precision control, the environmental controls that you get when you're confined to that little box. So we realized we need to think of other applications for this because there is promise. So we went to something that we're familiar with as architects, and that's concrete. And we said, okay, let's start printing with realistic building materials. So we made up our own concrete mix. It's a fast-setting cement with a styrofoam, it's like little microscopic styrofoam balls to make it really lightweight. And then when you add the magic ingredient of water, you get your concrete that sets within 10 minutes. This allows us to start to layer the material. And, we also looked at our good friends in the construction industry and saw what they were doing to move concrete. And they have a two-part system for large jobs where you have your concrete trucks that carry material and they deliver it to a pumper truck that then has an arm that moves around and starts to deposit it where you need the concrete. So with that, we set out to also design from the ground up our own 3D printer. And luckily, we were able to rely on the equipment available at our office. And everything in red was 3D printed in-house with our equipment. And simply, the feeder on top is your concrete truck. It has an Archimedes screw inside that mixes the concrete when it rotates one direction. And then when you reverse the direction, it starts to feed it into the conveyor, where we have another auger that's controlled by a separate stepper motor that start to push the concrete out. All of this is controlled by a really comprehensive grasshopper definition that our friend Tam developed. So every aspect of it is controllable. It's parametrically controllable by a slider. So if, for instance, we wanted to increase the payload capacity from 11 ounces to 11.5 ounces, the feeder itself would increase in size, and everything else would adjust to accommodate that. So we can, on the fly, change the type of material you want to print, or even the attachment devices necessary to affix itself to a new frame. So that kind of flexibility, and then using our own 3D printers, allow us to rapidly test different designs and models. I think we tested over 30 different iterations before ending up with what you see here. So this is a cutaway model that we did of that, so you can start to see the blades inside that convey the material. And we have a little pressure gap or pressure point that develops right before it reaches the PVC nozzle. And when we tell it to stop printing, that little pocket of pressure actually stops the flow of concrete and kind of plugs itself. So that was something that we hadn't planned, but it was kind of fortuitous when it happened. And let's see. So these are some of our lab tests that we've done with our little homebrew 3D or concrete 3D printer. And you can see the little styrofoam balls within it. And one of the important things is, since we're going to be layering liquid concrete on top of itself, the set time was really important, because it needs to set quickly enough that when the second layer of material comes through, it's not going to slump and flatten out and be completely worthless. So in our early testing, we were getting pretty decent results with the ability to start to layer multiple layers of material. And this, while we were upgrading that, we improved our hexacopter a little bit. We added a laser rangefinder, and as you can see in this incredibly scientific demonstration, as we fly over this object, the laser rangefinder is constantly pinging the ground and can detect a variation within 1/100th of a centimeter, and then tells the craft to maintain that altitude, and it avoids the obstacle and continues on. And this is going to be really important in future development as we are layering more and more material on top of itself. It needs to be able to adjust to the new build height, and now this laser can start to track what's being built and keep the copter at the level necessary to deposit the next layer in the correct location. So now I get to introduce you to Muppet as she is today. So MUP stands for Mobile Unmanned Printing Platform, and we added the "et" suffix to just indicate that she's a smaller scale version of what we envision to be an infinitely scalable device in the future. So here she is in all of her glory, flying up in the, where were we that day? Elysian Park? Yeah. So had a great view of downtown. We have now redundant GPS sensors, so if one gets a bad reading, the other responds accordingly and will take over control of the craft. And the nozzle and the printer itself is attached to the back with a laser rangefinder in front, so it's constantly keeping itself above whatever layer material is being added. So now we get into some quick applications of this technology, because this is the fun part, where you get to pretend we're in a sci-fi movie. So when we first looked at it, we saw a lot of humanitarian and construction applications for this. So if you have a natural disaster and roads and bridges are out and you can't get traditional shelters to people, you could send a few of these out. They could harvest a local build material and then mix it with some sort of inorganic binder or organic binder, and then build rudimentary shelters to allow people to look for loved ones, food and water, rather than also where am I going to stay tonight. So that's one aspect. And then for construction, you could use these for bricklaying activities. You could have some that are laying a bed of mortar while others are laying bricks. You can work on teaming them together to allow for longer flight and uninterrupted deposition of material. So think mid-air refueling like the military uses. You could have some UAVs that are specialized at carrying material and dropping it off in one location, others that are just refilling batteries or swapping out batteries while the other's in mid-flight. Also, there's some disaster preparedness or relief opportunities. In this example, floodwaters could be rising above the levee line, and you can't get tractors out there or bulldozers to bring a new layer of sediment. So you could send a whole fleet of these out there to protect your home from the impending doom. This is actually a real photo from Nat Geo from a flood in Mississippi. So we just kind of took some liberties. Also for exploration, you could send a few of these out a day's journey ahead of you. Then you don't have to carry your gear with you for tents and stuff. And when you arrive at your destination that day, there's a camp pre-constructed for you. Also, there's some industrial applications for this kind of technology where not necessarily layering and building up of material. You could then start to mix epoxies and deposit them to fix cracks in places that you normally wouldn't want to risk human life for repair. So all of this, again, is not without its challenges. We are kind of learning new ways to do things wrong as we go. That's our motto. And we just try to solve these problems. So we're currently dealing with an issue of the copter getting erroneous readings from the laser rangefinder, and it suddenly thinks it's landed, and it shuts the motors down. So it's actually, a foot off the ground, and then it just kind of, decides it's going to take a nap, which is what's happening in this photo. Also, our biggest problem that we're dealing with is vibrations, and anyone who does aerial cinematography with drones knows that vibrations are evil. So right now we have rigid connections between the printer and the frame of the craft. So all of the vibrations of the motors turning are just going right into the printer, and those vibrations act like a shaker table, and the concrete just starts to flow out on its own without us turning any of the screws. So moving forward, we're currently working on dampening vibrations and lowering our printer so that maybe if we get farther distance from readings to the ground, we're not going to get those bad readings, and it's not going to try to shut itself off in mid-flight. And that's what we're doing. Thank you.